Hello, I'm Guang from. I will now begin my presentation. The table of contents is as follows. This is the first question. I will explain the three rounds of the chicken game. The chicken game refers to a competition between two rivals that persists until one side collapses. In 1984, Japan initiated the first chicken game and starting a price war. As a result, Intel eventually withdrew from the memory semiconductor business. Korea, in response, adopted a stacked structure and expanded wafer size 200 mm, enhancing cost effectiveness. Consequently, Germany's Kimunda went bankrupt. Then, in 2010, companies from Taiwan and Japanese initiated the third round of the chicken game to overcome their accumulated losses. In response, Samsung and SK hynix make significantly investment in facilities, increasing the supply of DRAM and successfully fending off the competitions. As a result, Samsung and SK hynix and Micron, which had survived the previous rounds of the Seeking game, came to dominate the memory semiconductor market. First, this graph illustrates for the supercycle of memory semiconductor that has been ongoing. A semiconductor supercycle refers to the phenomenon where the development of new technologies and surge in chip demand lead to a rapid increase in revenue of related companies. Subsequently, revenue decline. This cycle repeats approximately every 4 to 5 years. While revenue periodically increase and decrease, looking at the long term, spanning to 10 to 12 years, the overall trend shows an increase in revenue. Next, let's make prediction about the future supercycle. In the field of AI, the development of various AI services, including ChatGPT, Alexa, and Siri, and the size of AI semiconductor market implement them are gradually growing. The Institute for Information and Communication Policy predicts that the size of the AI semiconductor market will increase by an average of 12 per year, reaching $86 billion by 2026. Next, this left image shows the types of semiconductor used in autonomous vehicle presented by Samsung Electronics. According to Professor Park Jae-gun, resulting in an estimated 8% will increase in semiconductor price corresponding to the overall cost compared to traditional internal combustion engines. Furthermore, data provided by McKinsey and Company predicts a steady rise in the automotive semiconductor market from 2019, reaching $280 billion by 2030. Therefore, with the future impact of AI and autonomous vehicles, it is anticipated that a stronger supercycle will emerge. Next, I will present on the second topic. Now, I will explain three types of FETs. The planar FET is a flat structure where the gate and channel touch on one place. As a semiconductor miniaturization occurs, the critical dimension decrease, and this leads to occurrence of short channel effect, and this resulting leakage current and reduced switching abilities. FinFET, designed to overcome the limitation of planar FET, is currently the most wide used type. It features a three-dimensional structure where the gate and channel meet. This increased the junction area and enhanced semiconductor performance. However, there is a limit to reducing the operating voltage beyond the 4 nanometer process. To address this limitation, gate-all-around FET was introduced. In GAA, the gate surrounds all around the channel through which the current flows. Additional GAA can be used in processes below 3 nanometers. However, it is still in the early stage of adoption due to technological challenges. Next, I will present the paper I found. This memory semiconductor has found questions related to how they actually use with FET. This paper studies the performance difference in SRAM. The journal has an impact factor of 3.56 and 17 citations. One of the performance metrics for the SRAM used in this paper's experiment is its stability. It is measured by static noise margin that is called SNM. SNM represents the maximum noise that the memory cell can withstand without changing its state. The method for measuring SNM involves connecting two DC noise sources to the inputs of two inverters, intentionally adding noise and then gradually increasing DC voltage at which the cell value is inverted. The measurement research shows that FIN-FET SRAM exhibit a larger static noise margin than planar FET at all temperatures. Secondly, let's talk about leakage current. First, the word line is set to 1 and the bit line is charged to 1, stalling 0 in the internal node. In this way, current flows from the bit line to the internal node, and when the word line is turned off to 0, at this moment the pass gate is open. However, at this point, the residual current remaining in the pass gate continues to flow, and this is measured to determine the leakage current. The experiment's results show that the lower leakage current was measured as SRAM using FIN-FET. Through various experiments conducted in this paper, it was concluded that FIN-FET can exhibit superior performance compared to SRAM using planar FET. Furthermore, this time, I investigate the performance of SRAM using FIN-FET and GAA. As a result, I found information on Samsung Electronics Tech Blog introduced by Samsung Foundry at ChipEX 2023. In semiconductor technology, controlling the transistor to align with the logic requires adjusting the amount of current. For achieve this, the width of channel needs to be dynamic changed. FIN-FET uses approach of increasing the number of fins horizontally to enhance the channel width. But this method has a limitation of being able to change only the integer number of fins. On the other hand, GAA allows adjusting the width of the nanosheet, providing various channel width options. And then, through this graph, it can be observed that GAA exhibits a larger light margin and a lower distribute margin than FIN-FET. Therefore, GAA can be used with lower power and is better in terms of performance compared to FIN-FET. During investigation into GAA, I developed a curiosity about the performance difference based on the channel structure. And then I found the following paper. In this paper, experiments were conducted to compare the performance of GAA channels with cylindrical and rectangular structure. The journal impact factor is 2.87, and it has been cited 17 times. In rectangular structure, large electric fields gather around the edge of each channel, and then it results a short channel effect, which can result in leakage current. However, in cylindrical structure, the electric field is uniformly distributed by symmetrical structure. Substrate swing represents the change in the voltage need for the semiconductor device to transition to a different state. DIBL refers to a phenomenon where as the drain voltage increases, the barrier in the channel lowers, making it easier for current to flow. Experimental research show that in the cylindrical structure, both SS and DIBL values are lower compared to the rectangular structure. This indicates that the cylindrical structure reduces the leakage current and enhancing the performance of device. The difference in the leakage current is approximately 5 times. So cylindrical channel shape can enhance the performance of GAA FET. In conclusion, synthesizing the finding from our investigation, the GAA with a cylindrical structure emerges as the most optical component in the terms of the performance. Lastly, let me explain about the next general FET. In 2012 at VLSI, the Belgian IMEC introduced CFET. The proposed approach by IMEC involves stacking NFET and PFET on the top of each other, shielding the source and drain and gate. According to DTCO analysis, CFET can achieve a half area reduction compared to a conventional GAA, leading it to increase the efficiency. Based on TCAD analysis, the proposed CFET can meet N3 goals in terms of power and performance and exhibits superior performance compared to FIN-FET. However, to implement this at 1 nanometer and below, several technological challenges need to be addressed. Some of these challenges include the absence of a lower metal layer for bottom device and the voltage drop from the deep via. Therefore, more research are needed to overcome these technological challenges. The sources used in the presentation are as follows. Thank you for hearing my presentation.